Some gas characteristics are: they expand spontaneously to the container, they are highly compressible, they form homogeneous mixtures with each other, regardless of the identities or relative proportions of the compound gases.
For the gas laws, you have Boyle's law, which is PV equals PV. You have Charles' law, which is V over T equals V over T. You have Gay-Lussac's law, which is P over T equals P over T. And you have Avogadro's law, which is N over V equals N over V.
Okay.
If you wanted to apply these laws, an example would be if you had a fixed quantity of gas at 23 degrees Celsius that exhibits a pressure of 735 torr and occupies a volume of 5.22 liters, find the volume the gas will occupy if the pressure was increased to 1.88 atm. So first you would have to decide which gas law you would need to use. Since it's dealing with pressure and volume, you're going to use Boyle's law, which is PV equals PV. Next you have to convert the 735 torr to atm because you want the units to be the same. So you divide that by 760 and you get 0.97 atm. Next you just plug the values into the PV equals PV equation. So you have 0.97 times 5.22 equals 1.88 times x. And then if you solve it all out, you'll end up getting x is equal to 2.68 liters.
Go ahead.
Okay. Another example of applying the gas laws would be if you had a fixed quantity of gas at 25 degrees Celsius concealed in a 5-liter container, and you wanted to find the volume if the temperature was increased to 30 degrees Celsius. Since you're dealing with volume and temperature, you're going to use Charles' law, which is V over T equals V over T. So then you just plug in the values. So you have 5 liters over 25 plus 273, because you want to use Kelvin, equals V over 30 plus 273. So you have 5 over 298 equals V over 303. And when you solve it all out, you get volume is equal to 5.1 liters.
So the ideal gas equation is PV equals nRT. P equals pressure, V equals volume, N equals moles, R equals 0.0821, and T equals temp in K. Okay, if you want to apply this equation, you can have 0.5 moles of a gas, which is a volume of 5 liters at 25 degrees Celsius, and then find the pressure of the gas. So all you have to do is use the Pivner equation. So P is our variable, we don't know what that is. We put 5 for volume, put 0.5 for moles, we put 0.0821 for the constant, and then 25 plus 273 for the temp, which would equal P equals 2.44 atm. Another example of Pivner is the one in front of you, where P equals 1 atm, volume is the variable you need to find, N is 0.7 moles, and R is 0.0821, and T is 298 Kelvin. So to solve this problem, you use Pivner. P equals 1, V is the variable we want to find, N is 0.7, R is 0.0821, and temperature is 298. And then when you add and you find it all out, it's 17.1 liters.
So to find the partial pressure of a particular gas, you take the total pressure of the gas mixture multiplied by the total mole fraction, which is the ratio of the number of moles of one component to the total number of moles in the mixture. An example of this concept would be if you had a mixture containing 0.538 moles of helium, 0.315 moles of neon, and 0.103 moles of argon in a 7-liter vessel at 25 degrees Celsius, and you wanted to find the partial pressure of helium. So you would first start by finding the total number of moles by taking 0.538 plus 0.315 plus 0.103, and you would get 0.956 moles. Next, you would find the total pressure using the Pivnert equation. So it is P times 7 equals the total moles, which is 0.956 times 0.0821 times the total temperature in Kelvin, which is 298, and then you get total pressure to equal 3.34 atm. Next, you would find the mole fraction of helium by taking total moles of helium, which is 0.538, over the total moles of the mixture, which is 0.956, and you would get 0.563. Next, you would take the mole fraction multiplied by the total pressure, which is 3.34 atm, and that will equal the partial pressure of helium. And if you solve it out, the partial pressure of helium is 1.87 atm. Another example of partial pressures could be if you had 0.206 moles of helium, 0.417 moles of neon, and 0.183 moles of argon in a 5-liter vessel at 25 degrees Celsius, and you wanted to find the partial pressure of argon. So first what you have to do is find the total number of moles. So you take 0.206 plus 0.417 plus 0.183, and you add them up, and you end up getting 0.806 moles. Then you want to use Pivnert to find the total pressure, so you have P times 5, which is the volume, equals total number of moles, 0.806, times the constant, which is 0.0821, times temp in Kelvin, which is 298. And when you solve it all out, you get P is equal to 3.94 atm. Next, what you have to do is find the mole fraction of argon. So you take the moles of argon, which is 0.183, divided by the total moles of the mixture, which is 0.806. When you solve that out, you get 0.227. Next, you take the mole fraction and you multiply it by the total pressure of the mixture, which is 3.94. When you solve that out, you get the partial pressure of argon equals 0.89 atm.
Some things to remember about non-ideal gases is that gases tend to deviate from ideal behavior at very high pressure and very low temperature. Also, real volumes of gas molecules and attractive intermolecular forces between molecules cause gases to behave non-ideally.
The kinetic molecular theory helps us understand what happens to gas particles when experimental conditions are changed. The kinetic molecular theory states that gases consist of large numbers of molecules that are in continuous random motion. The combined volume of all the molecules of the gas is negligible relative to the total volume in which the gas is contained. Attractive and repulsive forces between the gas molecules are negligible. It also states that energy can be transferred between molecules during collisions, but the average kinetic energy of the molecules does not change with time as long as the temperature remains the same, and the average kinetic energy of the molecules is proportional to the absolute temperature.